Hello and welcome to a webinar about LTE Advanced technology aspects. My name is Schulford. I'm a technology manager at Rohde&Schwarz. So today I would like to give some technology aspects of the LTE Advanced features. So what are the latest release features and what are the technology aspects in LTE Advanced? So there are a lot of features, as we can see in this figure here, which is a diversified scheme, many different features, and we see the evolution of LTE. So started as a packet switched data network, then introducing new features like voice over LTE, broadcast concepts, high data with carrier aggregation, and so on and so on. But what you can see in this picture as well is, let's say, a structure as known from the IMT 2020, which is our very famous triangle of services, which is the enhanced mobile broadband on one corner, which is the massive machine type communication as service, and also on the other side it is the ultra reliable and low latency aspects, which is definitively known in the background of 5G. Yeah? But here on this kind of classification of the features of LTE Advanced, we see a similar structure. So let me comment this with the words like LTE Advanced is trailblazing the road to 5G. So LTE is there to stay, and LTE will coexist and continue in combination with 5G. So what are now the features of the LTE Advanced Pro? And I would like to continue the webinar with this structure of our triangle with describing the services. So let's have first a look into the service aspects of the machine type communication. Massive machine type communication. So what are the technology aspects in LTE? So starting from first LTE on the left side, where we have our categories, the standard, let's say, LTE model for high data rates, yeah, with a full bandwidth like 20 megahertz, then later on features carrier aggregation and so on and so on. Few years ago in release 10, release 12 and so on, 3GPP introduced some kind of new categories on the device side. First the category M, which is a shrinking bandwidth of 1.4 megahertz only, and especially a so-called half duplex mode. That means the device is either transmitting or receiving, but not simultaneously. So we reduce the complexity of the devices. Another motivation aspect is the coverage extension. So the idea is to bring radio coverage in a wide cell coverage, cell size, and also B going into the buildings for indoor coverage. And in another mode, very famous, is the introduction of Narrowband IoT. So another continuation of much smaller bandwidth. Here Narrowband IoT of, let's say, 180 kilohertz bandwidth. And it runs in different modes, either a standalone mode, it can run in a combination in-band mode in LTE band, or it can also be deployed into the guard band of LTE. Yeah? So what are now release 13, 14, what are now the next step in enhancing and updating those technology aspects? So what's going to happen in release 14 in Cat M? Yeah? We see a few aspects. Let's say important is in Cat M that we go back and increase the data rate. That means increasing the bandwidth. So started first Cat M1 with 1.4 megahertz, and now category M2 is supporting a bandwidth of up to 5 megahertz. So the idea is for machine type communication to have a high data rates. Yeah? This is then also described with new categories. Another modification aspect is kind of mobility support, better support, then the introduction of voice call. So careful, this is not a competition to the traditional smartphones where we have high definition voice, so enhanced speech codec. This is more or less the idea. You assume like a CCTV camera, for example, where you can now establish an audio channel. So just some basic audio for basic communication. And also another feature that is introduced now in the next generation of the Cat M categories is the definition of positioning. So support of device positioning based on radio technologies. Later on, a few more words on that. Narrowband IoT is also undergoing some enhancements and some evolution, which is a slightly higher data rate. So careful, there is no bandwidth change. It's still 180 kilohertz, but with a kind of combination of HARC process and a larger transport block size, we can obtain a little bit higher data rates for those. Yeah? Another aspect is a much higher number of devices per area. So let's say different deployment scenarios where we have different channels for Narrowband IoT, and the network can schedule the data in different channels, so allow more devices per cell, reducing the complexity of a device with another power class. And also what I just mentioned for LTE-M is the positioning aspect. Yeah? Later on, more words on that. So just a few examples. What does this mean, high data rate or higher data rate? Sorry for this. Narrowband IoT downlink. Yeah? So compared to release 13, where it has been one HARQ process, so one packet send, acknowledgement, and possible retransmission. Now in release 14, we have the possibility of sending a larger transportation block size. That's one modification. And the other modification is in release 14, as you can see in this figure, is that we have two packets sent, more or less continuing each other, succeeding each other. And that means we are running two HARQ processes in parallel. Yeah, so this allows a slightly higher data rates for these machine type communication devices. On category M devices, higher data rate is obtained, as I just introduced, with a wider bandwidth. And for here we have to understand the concept of Cat-M, which is a 1.4 megahertz carrier, which is known as a narrowband, the NB abbreviation you see in that slide. So narrowband 1.4 megahertz. And now for obtaining higher data rates, it is the possibility to combine several of these narrowband carriers to have a maximum bandwidth of 5 megahertz. And this is what we see in these tables here, this different kind of allocation of resource blocks. So the maximum number of resource blocks that can be scheduled to one device is here 24. And this runs in addition with kind of CE, so coverage extension mode. And the idea is with coverage extension is to have a kind of number of autonomous repetitions. And due to this, we improve the coverage, especially for indoor operations. Yeah? On the other side, of course, this causes an effect on latency. As clear, more repetitions means that one packet duration is much longer, but this is not the focus for Cat-M or for Narrowband IoT. Latency is not the main focus. So we talk about so-called delay-tolerant services. Yeah? So here, just a summary. For these devices, category M2, the number of HARC processes can be extended up to 10, and the bandwidth can be extended up to 5 megahertz, and also the possibility of a larger transportation block size. New features in category M and Narrowband IoT is, let's say, new feature for them, but an old feature already known from the traditional LTE. And this is the idea of positioning. Yeah? And here 3GPP introduced the known concept of OTDOA, which means observed time difference of arrival. What does that mean? We assume we have a mobile device, and this can receive a downlink signal coming from one cell, and this downlink signal does now contain a new type of reference signals, these PRS, positioning reference signals. And the device is capable to measure the time difference between different PRS signals coming from different cells. And this is shown here in the left part of this picture, where we can triangulate different signals. So the delay time is measured and reported back to the network. And based on this triangulation, the network can now calculate the position of a device. So advantages, this runs completely based on LTE, Cat-M or Narrowband IoT and does not require any additional positioning method like, for example, satellite support. For sure, just remark, please note, it is not forbidden to have a satellite receiving chip inside the Narrowband IoT device, but that decision would be up to the manufacturer. But it is not defined by 3GPP. Okay, so this was about the machine type communication. Another big block in our triangle of services is this enhanced mobile broadband. So trailblazing the way to 5G and to see how can we get a much higher data rate in LTE Advanced. So what are some technology aspects? First, we have new user equipment categories which describe the support of high data rates. So what is new? I'm not going to read this table with all the numbers. You can find it also in some of our white papers. But here the main difference is that started from release 8, now in the latest releases, we have a split between a UE category for downlink and a UE category for the uplink. Yeah, so it's kind of two parameters. The UE describes its category, uplink and downlink are separated. Yeah? A big discussion and lots of work has been done in getting additional spectrum. And here especially we have the whole background of the unlicensed spectrum, the ISM band. Industry, scientific, medicine bands, especially the one shown here in this example is the 5.9 gigahertz ISM band. I have here a picture about the frequency allocation. This is typically like here the wireless LAN channel raster used in the 5.9 gigahertz range. The agreement of LTE 3GPP is to use the same channel raster. So if we assume we are deploying a 20 megahertz LTE channel inside the ISM band, it would have the same position at the corresponding 20 megahertz wireless LAN channel. And this is to kind of coordinate between each other and to coexist and to avoid too much interference. But the big discussions will be how can we use this unlicensed spectrum. And let me try to give a summary on overview in this kind of using unlicensed spectrum. What are the different methods? The first method, this is also very old, known in LTE in several evolution steps, started from release 10 up to the later release, is wireless LAN offloading. So the basic idea is I have an ongoing data connection on LTE, maybe run multiple connections in parallel, and due to get more capacity, some of these data connections will be offloaded into an existing wireless LAN network. Yeah? There has been also lots of discussion, lots of evolution aspects in that. Another feature is this LWA. This is, let's say, a continuation of the dual link connectivity. So dual link connectivity in general means one LTE link together with another LTE link. And here the enhancement is that instead of using one link LTE, which is the master, we will now allocate a second link, but which is now running on wireless LAN technology. So that is a kind of cooperation between LTE and wireless LAN. And then as a third aspect, we see here in the center this carrier aggregation, or LAA. This would be the enhancements of carrier aggregation, but with the aspect that one or multiple carriers will operate in the unlicensed band. And this is known in LTE as LAA, LTE unlicensed. Yeah? So here is the idea that we use carrier aggregation in release 13 with some carriers running in the unlicensed band. What is new in release 13 is the possibility that we also have an unlicensed carrier in the uplink. So a UE does not only do carrier aggregation in downlink unlicensed, but also will do an unlicensed carrier possibly in the uplink. But we still have the issue, what about possible interferences between wireless LAN and LTE? And this has been lots of discussion, and the agreement is the following: to introduce an algorithm, a concept that is known as listen before talk. So before transmitting an LTE data packet, the transmitter has to do a carrier sensing. So check if the carrier is free, if it is occupied or not. And if it is free, if it is available, then we are allowed to transmit. And this is shown in this diagram, in this algorithm that runs in several steps, a kind of first carrier sensing. And if the carrier is free, after a certain kind of delay or occupancy time, the carrier will be checked again. And this is then this ECC8, this enhanced carrier sensing mechanism. So then the device or the transmitter would have to check the carrier again and again. But what are now the consequences for the LTE? If you assume a base station, like a small cell, in a traditional LTE cell, the carrier in downlink is always on. Yeah? The bandwidth and the reference signals, the broadcast control channel is always on air. And that concept has to be changed. So for that reason, we are now introducing a kind of new frame structure, so frame structure type 3, which is a kind of fragmented time occupation. And that's shown here in the upper part of this slide, where I'm showing you, like here, hopefully with the red dot, you can see that we have first here the blue part, which is a short listen before talk. Then we have a new signal, this DRS. I'm coming to explain that very soon. And possibly here on the middle part we see listen before talk. That gives us a clear, the channel is available, and now we have a kind of downlink subframes that can be sent. Important to understand is that this transmission lasts only a certain amount of time, which is described here as maximum channel occupation time. And this is explained in the lower part of the figures with the different timing rules. Yeah? So what is the time for the minimum averaging time for getting the rules if the channel is free or not? So this is based on some power threshold values. This is based on a timer where the device transmitter has to average the power levels and so on and so on. Then we have an additional back-off timer. We have the maximum channel occupancy time and so on and so on. So going into more details on that. On the other side, what is the consequence? As I just explained, compared to a traditional LTE cell, which is always on air, so that means it can always be identified by a UE. So if you assume a small cell that is always on air, it can always be identified, assuming we have the possible, the right coverage for sure, but the signal is always on air. And this is changed or different for LAA. So for this reason, 3GPP introduced a new type of reference signals, which is this discovery reference signals. So we can understand it as a kind of periodic short burst signal that is transmitted from time to time in a periodic manner. And this helps the device to synchronize to such a small cell much faster and to not waste too much time for the transmission of LAA. What are additional aspects in LAA? Something like here, this is maybe coming more from the regulatory issue. So just the story behind is that regulatory of using the unlicensed band. What means unlicensed? Yeah? Unlicensed means you can use the spectrum for whatever you want as long as your transmit power stays below a certain threshold. But what is now the definition of this power threshold? This is typically defined as the average power density versus a certain bandwidth. Yeah? And to avoid or to overcome that rule, 3GPP introduced now for the uplink of LAA, so a UE will transmit in the unlicensed spectrum a new kind of waveform that is no longer contiguously allocating the resource blocks as we do it in traditional LTE. We have now here on the right side of this curve, you can see this kind of interlaced waveform. So just as an example, shown here in this figure with some kind of interlaces, I would have a bandwidth of, let's say, 20 megahertz, and I will allocate 10 resource blocks to that device in uplink. So now the allocation is not 10 contiguous allocated resource blocks, but the resource blocks are interlaced. Let's say one resource block per spectral fragment, and the consequence is that we have a less spectral power density within a certain bandwidth, and we do not violate with these regulatory conditions. The other mechanism I introduced in the beginning is this cooperation or combination between LTE and wireless LAN. And this is now in release 13, 14 introduced as LWA. So how does this work? It's a dual link connectivity. So we have LTE, radio connection, ongoing and behaving as the master. So all layer 3 control and data is running over LTE. For more capacity, we now add a second link, and this link is running over wireless LAN. So this wireless LAN terminal and access point is coordinated from LTE, and also the connections to the backhaul network is coordinated by the LTE base station, the eNode B. For kind of encapsulation and tunneling of the data, 3GPP introduced a new protocol that is shown here as LWAAP. So it's a kind of encapsulation of an LTE data packet with an LTE IP header, and this will encapsulate it into a wireless LAN MAC header to run in a tunnel process through the wireless LAN network. Okay, and this also supports certain mobility issues. For example, several Wi-Fi access points, wireless LAN access points, can be coordinated as one WT, and the change of the radio link from wireless LAN to another wireless LAN access point is no longer coordinated by the LTE base station. This is running smoothly and seamlessly. Only if we have, let's say, a higher mobility from your device, and then we have to change the LTE with a link with this wireless LAN mobility. What are additional aspects in LTE? Of course, high data rates. And this is a big motivation, or has been a big motivation, for carrier aggregation. That was introduced in release 10 already, and you see it here on the left side of the slides with these different application modes, let's say in the in-band, intra-band with contiguous allocation, intra-band with non-contiguous, but also inter-band allocation. So that is known in release 10, first started with downlink carrier aggregation, then later introducing uplink carrier aggregation. Release 12 continued with a kind of mixed operation mode, that one component carrier could run in the FDD band, another component carrier could run in the TDP band, so just to use the spectrum more efficiently. And what are now the latest release in release 13 and 14? It is to increase the number of component carriers. So we say beyond 5 component carriers and going up to a maximum number of 32 component carriers that can be allocated. What are the major consequences by that? It's not only the increased bandwidth, it's also now, due to more data rate in downlink, we require more signaling, especially if you consider the HRQ process, the feedback, acknowledgement, not acknowledgement. So therefore we need more capacity. And this has been considered in 3GPP with either a new PUC format, so offering higher data rates for the acknowledgement, but also the possibility that there can be 2 transmissions of PUC. So that means 2 radio links in uplink have to be supported by the device for providing more capacity in the uplink. So these are the major aspects of carrier aggregation enhancements. And beside lots of theory and lots of slides, I would like to hand over to my colleague Manuel Galossi, who has prepared a practical setup and would like to see how this works in live for enhancements of carrier aggregation.
So here we are live at the test system, and as discussed in the webinar, one major aspect in testing of LTE Advanced Pro modules is enhanced carrier aggregation. So the testing of 5 carrier aggregation in downlink or more. As a test system, we are using CMW 500 in a multi-box environment, and specifically this use case here is testing 8 component carriers in the downlink, using only 2 CMWs and the controller unit on top. As a test mobile, we are using the Prisma device over here, which is directly connected to the 2 CMWs. As a test application for this 8 component carriers carrier aggregation test, we are using our RF testing environment, commonly known as the CoreBox application. And as you can see here in this window, which is being used to set up the network configuration and the parameters of the component carriers, we have set up 8 component carriers which are using here different bands. The cell bandwidth is set to 20 megahertz, and we are currently using a configuration of 2x2 MIMO, which means we reach up to 200 megabit per second per carrier, times 8 would result in the 1.6 gigabit per second here on the physical layer. If we go down here to this RX measurement window, you can measure the overall throughput here on the layer 1. And as I said, theoretically we would reach up to 1.6 gigabit, which is here the case. And if you want to see the throughput of the individual carriers, you see we have here almost 200 megabit per second in the downlink. In parallel, you could also use the TX measurements to monitor the RF characteristics of the device under test in the uplink. And here we have a live measurement of EVM, the IQ diagrams, power dynamics, or the resource allocation tables in the uplink. This was our demonstration of 8 component carriers in the downlink, and now let's continue with the webinar.
Additional technologies, especially for high data rates. And this sounds, on the first glimpse, sounds to be like a crazy idea. Multi-user superposition transition. That means we are using the same radio resource for multiple devices in the same time in the same frequency. In a simplified picture, it's more like the idea to use the transmit power difference of different devices as a kind of method to separate the radio signals of each other. And this is shown in this figure here. So assuming one cell, and I have one UE that is at the cell edge, and I have another UE that is near, in a near and far situation. And that means from a transmit power perspective, to talk to the UE at the cell edge, you have to transmit with a higher power, and to talk to the UE which is close to you in the near distance, you can lower the transmit power for this part. And this led from the academic part to the introduction of kind of successive interference cancellation mechanism, and also to the idea of superimpose the radio signals together. So how does this look like? Yeah, like shown here in this picture, and maybe I'm using now my laser pointer to see. I have here 2 devices, a blue color and an orange color device, and both of them are running, and I have here the example of a QPSK modulation scheme. We can see the vector, high power, and the orange color is the near UE, which is a lower power, and now is the idea to combine a modulation scheme, and I would like to avoid the term 16 QAM, but it looks like a 16 QAM allocation scheme. But what is now the difference? If you consider the blue color, the first 2 bits, which are identical in this quadrant, so the UE that has, let's say, a adverse signal-to-noise ratio does not need to identify these 4 constellation points of each other. It is fully sufficient to recognize whether it's this quadrant or this quadrant or this quadrant or the other quadrant. Meanwhile, the other UE, here the orange color, that is the UE which has a better signal-to-noise ratio, and this is capable to separate the various 4 constellation points of each other. So we can see how the principle works, and on the receiver side, we are introducing now this kind of interference cancellation mechanism, yeah, which runs in the following way. You assume you get a complete sum signal that contains all the user components together. So a small part of that signal, that's your own signal. The other part of the signal, that signals that belongs to other users. So now how are you working? And the idea simplified is the following. You try to decode and demodulate the strongest power component of that signal. And you demodulate, you decode, and then you check whether it belongs to you or somebody else. Assuming it's signaled for somebody else, and now instead of just discarding it, we are doing another trick. We take that signal component, let's say like the IQ signal, and we are regenerating it again. So more or less like rebuilding the signal component itself, and in the mathematical term we call it inverse. We are inverting the signal, and that's shown here on the right side of this picture. Here the minus and plus, that means the original signal is combined with the inverse of the interference signal, and that means we subtract the called interference signal from the total signal amount. And the result or the remainder of the signal is now feedback and will be the input of the next receiver. So you can understand it as a kind of cascaded structure of multiple receivers, and more or less the first receiver tries to reduce the first interference signal, and the result is the input of a second receiver. And this output is the input of a third receiver, and so on and so on and so on. Shown in the lower part of this slide, hopefully you can see my red pointer, this is the advantage we can get. Here as an example are 2 users, and if they are not symmetrically sharing their radio resources, but using the advantage of sending a slightly higher data rate to the UE which has a better signal-to-noise ratio, then we can achieve the overall capacity of a network. How is this realized now in LTE Advanced? This runs in different categories. I only introduce it in short. The first category is two UEs which are superpositioned with each other in a kind of constellation mix of the QPSK or 16-gram diagram. Here in this category 1 signal we see the following, so like two QPSKs will be combined with each other, but the resulted constellation diagram does not follow this gray coding. Short reminder, what does it mean gray coding? Here in the right corner you see that signal 0, 1, 1, 0 constellation symbol, and two direct neighbors, that one here and that one here, are differing in more than two symbols. So the gray coding means that we have a constellation pattern, and from one to the next neighbor signal the maximum distance of symbols that are differing is reduced to 1 to minimize the overall error. So here that finalized constellation of the bit patterns is not gray coded, which is different in the category 2. So category 2 is a similar procedure, but the bits will be shuffled and reorganized in this constellation pattern that it fulfills the gray coding mechanism. And the third category of a device is this category 3, which continues in enhancing the method of using a signal-to-noise ratio good device compared to a signal-to-noise ratio bad device in allocating more bits. So in the previous categories I introduced the example of having one UE with QPSK, that means 2 bits, and the other UE 2 QPSK, also 2 bits. So finally the 4 bits from a 16-gram constellations are split in 2 and 2 bits for each UE. And this is different in this category 3 component here. So I can give as a cell, as a base station, more capacity to a UE that has much better signal to noise ratio. And this is shown in this slide. For example, I have here 4 bits given by the 16-gram constellation, and 3 of these bits, the red color bits, are allocated to one UE, and only 1 bit, the blue color bit, is allocated to another UE. Yeah? So think at the overall capacity and not being selfish, and at the capacity of one single UE that has to increase the data rate. So the goal of MUST is to improve the overall network capacity that can be used in downlink. Another feature I would like to shortly introduce is this kind of broadcast update. In release 9 already in LTE we introduced MBMS, Multimedia Broadcast Messaging Services. But let's say, what are the drawbacks? MBMS requires a large area, this MBSFN, so several cells belong to that area, and the broadcast of the content, the data content, is the same content over a certain area. This requires a synchronization between the cells. And also it requires the same radio resource allocation per cell, and all cells belonging to this MBSFN areas have to allocate the same radio resource. Now, as a kind of change or an updated mechanism, we introduced SC-PTM, single cell point to multipoint. So first change is that the radio resource are used only within one cell. Of course, a neighbor cell may use the same radio resource. This is up to the situation, but it's not mandatorily. Yeah? Also, for that reason, we do not need a common time synchronization between the cells. So we have a more flexible allocation of radio resources for this broadcast and multicast mode. Typical application and a big demand is what we see in the machine type communication. Just a simple question: how do you do a software update on a machine type communication device? Assuming we have a sensor that has no user interface, MMI, to a human person, it is not operated by a human person, and you want to do a software update. Yeah? So how do you contact the device, and how do you do software updates of, let's say, thousands of devices in that cell? And for this concept, the SC-PTM would be the perfect solution. Yeah? This requires introduction of a new channel structure. Keep it short, we have here a new traffic channel. This is this SC-MTCH we have for the allocation and the signaling and describing the content, what broadcast content. So assuming in the old-fashioned style, a newspaper that gives you the information what is shown on the television today. Yeah? And this is what's here on this SC-MCCH. So it's a broadcast control channel that indicates what type of content is broadcast, is sent, and then the receiver can decide whether it is interested in that type of content or not. There are several identifiers introduced to have this group communication, so multicast, so we can combine different UEs into a kind of group, and this is this SCRNTI that schedules allocation of traffic channel on this SC-PTM, on this cell broadcast mode. Just as an example here in a certain message flow, on the higher part we have first how does the user equipment know that the cell supports this SC-PTM broadcast. This is indicated with a new system information block, SIP type 20. Yeah? On the network side we have in the core network the decision maker, the broadcast center that now decides this data content is running over SC-PTM. Then we inform the cell, the eNode B, that should start an MBMS session for SC-PTM and send out a notification report to the possible UEs who like to receive. Yeah, and this is this SC-PTM configuration message that is sent out to inform how the radio resource for this broadcast multicast look like, and later on we are running in downlink receiving this kind of operation mode. And this is shown in the lower picture where I have a typical LTE frame structure, the 10 subframes. Just a short reminder, the green color are forbidden for SC-PTM because they contain LTE reference signals, PBCH, SS, PSS, and so on and so on. I have the red color. That is an example of running concurrently MBMS, certain subframes. Yeah. We have the orange color, which are subframes that cannot be used for SC-PTM as they contain system information broadcast and especially paging. But then let's take here this short example, the blue color, which is split. Some of the radio resources are used for traditional LTE scheduling, the dynamic scheduling, and other resources are now used for SC-PTM broadcast. So for this we have via DCI scheduling, using this group identifier, the scheduling of the control channel of SC-PTM. And in addition, we have the scheduling of the SC-PTM data using this SC-PTM traffic channel. So that is the idea of broadcast on a cell-specific level. Yeah? Quick introduction into another concept, but let's say this is very important feature of 5G, massive MIMO, but also here another statement that 5G is not the only technology and LTE is preparing the way. The idea of beamforming, massive MIMO, is not a new idea in 5G. This idea has started already in LTE. Yeah? So from release 8, we introduced spatial multiplexing. Yeah? Release 10, increasing spatial multiplexing to 8x8 MIMO, and then new reference signals for channel status indication and demodulation reference signals. Release 13 and 14 are now taking this idea and enhancing it much further. So it's now the possibility to run a kind of antenna array in the base station, yeah, and to do beamforming in the cell in the base station, and to support the user equipment, we have now the possibility of sending CSI reference signals. So this is a channel status information reference signals that can be beamformed. So that would be the idea that multiple beams in one cell, and each beam has a specific CSI and can therefore be identified and reported back to the network to answer the simple question, what is the best beam? Yeah. On the other side, we also have a much better enhancements in pre-coding. So based on the PMI, the pre-coding feedback from the UE, the network can decide what is the optimized pre-coding mechanism. Yeah? And also this runs in combination with a much higher number of antenna ports. So release 14, we may have up to 32 antenna ports, so to distinguish different beams. Each beam may run on a certain antenna port, and then to use also full dimension MIMO. That means beamforming either in horizontal or in vertical or even in a combined way. Yeah? And this idea will be continued in 5G, but that would be another topic for another webinar. Yeah? What happens in the uplink with LTE Advanced? Just short, also we would like to increase the data rate in the uplink. especially for some kind of service. If you think at a simple video stream, you're watching a video from a server, video server. I'm not going to name which companies provide that. So you're downloading a video, but that means your uplink is not quiet. Your uplink still has to send feedback, like TCP/IP acknowledgements. And if you have a high data rate video downlink, this requires also a higher data rate on the uplink. So here now in LTE Advanced, we increase the data rate in uplink, for example, with carrier aggregation uplink introduced already, with a new modulation scheme, 256 QAM in uplink, but also in the TDD, TD-LTE, we are allowed to push the uplink traffic in this so-called special subframe. Coming to the third section of my triangle of the structure, which is this ultra reliable and low latency. And here for LTE, there's one famous example, which is the automotive sector, vehicle to X. Yeah? So vehicle to infrastructure, vehicle to vehicle, etc., etc. What is the answer on LTE vehicle for this? Keep it short. First, we are running LTE vehicle in a new frequency, which is targeting at the 5.9 gigahertz frequency band. We have to assume the following option. Two cars are driving. Let's say if you assume a remote area, so I'm not talking about downtown Munich, where Rohde&Schwarz headquarters is, but if you think at a remote area, in the desert area, two cars are driving, and you assume we have no radio coverage. But you still want to communicate, so therefore the enhancements of this side link. Side link has been introduced in release 12, which allows a device-to-device communication like you know it from your traditional classic two-way radio. And this side link operation mode is now updated to be used for vehicle devices like a car, like an infrastructure, a roadside unit, or even pedestrian, etc., etc. So the question will be how this radio resource for this side link will be allocated. For this we require a kind of external clock. So introduction of GNSS, so satellite will give the reference clock. We also have an enhancement on the infrastructure, especially if you assume two cars and the drivers, and they may belong to different network operators, so PLMN. That means we may have to introduce a kind of inter-PLMN communication. What else is new or not new? But if you assume a car, a vehicle is driving, maybe with a higher speed, so then we have to compensate a much higher Doppler shift. And this is taken into account in LTE Advanced for LTE vehicle with a higher placement of reference signals. And you see this here in this figure, the red color are additional DMRS, so demodulation reference signals. So we kind of sacrifice the data for introducing more reference signals to compensate a much higher velocity, a much higher Doppler shift. Yeah? And also the same idea as just introduced with SC-PTM, the idea of sending data to multiple receivers. So like here we introduce a kind of group identifier. This is this abbreviation TMGI. So sending the same data packet to multiple receivers. How does the allocation look like? And here in LTE vehicle we have two kind of transmission modes. Allocation. The first more or less is like, let's say, started from the traditional LTE. We have a coordinator, our base station, the scheduler, and the scheduler talks to the two devices. Here in my example it's two cars, and the radio resource that is used on the side link that is shown on this figure as the PC5 interface, and this radio resource is allocated via DCI control messages coming from the base station, from the eNode B. And this mode is known as TM3, Transmission Mode 3. There's an additional mode in separation to this, and this assumes we have no radio coverage. So two cars are driving in a, let's say, isolated remote area, and we assume we have no radio coverage. So now how is this radio resource for the PC5 used? First, the radio resource is to be used is indicated via previous system information broadcast. So the network will provide a kind of pool of radio resources that can be randomly selected by the two devices that would like to communicate with each other. To keep the time synchronization, we use the satellite, GPS or Galileo or GLONASS or whatever else are the GNSS services, and we use them for time synchronization, and the two devices will go into a two-way radio mode to allocate the radio resources of each other. So this is this kind of radio resource pool that can either run in the FDD, then the side link connection is used in the uplink radio resource, or in TDD it's the same, but then the two devices will run in the TDD uplink radio resource for communication via the side link. But again, lots of theory, lots of slides. I would like to hand over once more to my colleague Manuel to see how this LTE vehicle runs in live with a short demo.
This test setup here is showing a real use case for device testing of LTE V2X using the CMW500. One operation mode of LTE V2X is the usage of transmission mode 4, which means that there is no real network involved and the participants, like cars, pedestrians, are talking to each other without the network involved. Special use case of this demonstration is that the CMW500 in this case is not being used as a network emulator, it's being used as a participant within the V2X scenario. The device under test is here characterized with this emergency car, and for synchronization we are using a GNSS simulator, which is our SMBV 100 here. The use case of this scenario is whenever I press the button here, the V2X module, the real module, is sending ITS data over the PC5 side link. And the CMW500, here shown within this dashboard, then shows that there's, for example, here this emergency vehicle behind me. So this is a kind of use case to show LTE V2X together with the CMW500.
Okay, coming to the last slides of this webinar, just as a quick outlook, what I said in the beginning, LTE is here to stay. And LTE is going to continue, even when we have released 15 features, mainly known as 5G, with the introduction of 5G, but release 15 is still continuing with LTE, and we see a lot of, let's say, technical blocks where LTE is going to be improved and enhanced. Like small cell capacity enhancements, we have definitively a kind of connectivity between the LTE infrastructure and the new 5G infrastructure. We do some enhancements for the LTE vehicle, especially for much higher data rates and carrier aggregation on the side link, but also some improvements on the machine type communication. Just two examples, what is going to change in the next for Narrowband IoT. Some building blocks is, for example, the idea of a very early data transmission. So not going through the full signaling process with radio connection establishment, but immediately sending a random access followed by a data packet. Narrowband IoT is going to be supported by TD LTE operation. We support small cells for smaller power class. Yeah? There is a kind of discussion about the so-called wake-up signal. How do you understand this? Maybe some of you remember UMTS, 3G wideband CMA. I've been a trainer for this for a long time. So there has been a paging indicator channel. So that means like an indicator channel that only informs that there is content on the paging channel. And this is the similar idea like a wake-up signal. So just inform that there is possible information inside a paging that you should read. Yeah? And also some range extension, again, coverage extension mode with much higher number of repetitions, with power class modifications. These are currently the discussions for Narrowband IoT. And for category M, LTE-M, similar aspects like a very early data transmission, this wake-up call. Then there is a kind of request for higher UE velocity. So if you think at a machine type, a device that is placed, let's say, in a train, in a vehicle, etc., with a higher velocity. But on the other side, also complexity aspect is with a lower UE power class. Yeah? So this has been just in short described certain features of LTE Advanced. I do apologize for all those features which I was not able to talk about due to lack of time. For those of you who like to learn more and get more information about LTE Advanced, please have a look at our website. You see here the QR code, and also there is a white paper where you can find more information on LTE Advanced. Thank you very much for your time. It was a pleasure talking to you. Goodbye.